Mrs. McBride, I don't think that we can hear you.
Mrs. McBride. Can you hear us?
Can you hear me now?
Yes.
Yes.
All right, let's try again. Can you hear? Are you good now? So differential equations are an important part of Unit 7. So this is one of the final units that we are going to be looking at. The unit here is going to allow us to find all of those key features. It's going to allow us to find the C value. We're going to put the Y's on the left, the X's on the right. We're going to have a constant that might get plugged in and allow us to find the original function. These are the ones where you have e to the x and you solve for c, which is your initial condition. So we're going to look at exponentials today. And again, the idea behind a differential is that we are separating. You're going to be separating the x's and separating the y's. So solving a differential equation would look like this example here. You have dy dx on the left, and you have a function on the right, maybe f, maybe g, and the functions are in terms of x and in terms of y. So our goal is to get the gy function on the left, the f of x on the right, and you're also going to multiply both sides by dx. So you're going to divide by gy and multiply it by dx so that we can get the y's and dy's together and the x's and dx's together. So now we have our integral, our y function, our variable with integration dy, and then over here, our integral, our function, and our integration value dx. And then what you're going to do is integrate both sides entirely separately from each other. Exponentials are very similar. You're going to have your dy dx. It's going to have a constant, and then it's going to have your y function. So we're going to rearrange that so that y can be on the left, k can be on the right. And then this is the case where as you work through it, you end up getting a natural log with your y's, which means you have to, because you have 1 over y dy equals k dx. And then what happens is after you take your integral, you get the natural log of y equals kx. And then we want to solve for y, so we e both sides. And that's where the e to the kx comes into play. Now, anytime we take an integral without a bound, we have our plus c. And over here, when you take your e to both sides, your plus c goes up into your exponent. But the rules of exponentials says that's really like e to the kx times e to the c because we add them. And e to the c is really just representative of a constant. So that y naught can look like a c or a y naught in front of our equation. So that's where this equation gets derived from using exponential modeling. So all of that work in red is how you get to that box. So taking that last example we just looked at, the next part of that problem was part B that says write an expression for y equals f of x by solving the differential equation dy dx equals x square root y with initial condition. So part A was the derivative aspect for you. It was making sure you understood your properties of derivatives. Part B for this free response is saying, okay, now do you understand your properties of integration? So we're going to leave the x over on the right. We're going to multiply both sides by dx. And then we're going to divide both sides by square root y. So that gives me 1 over the square root of y times dy equals x times dx. And then I'm going to integrate both sides. So again, the square root of y in our denominator is kind of like y to the negative 1/2. And then over here, that's just our x dx. That one's rather easy. So remember the rule for integration is you add 1 and then divide by your new exponent. So we add 1 to negative 1/2 and we get a positive 1/2. So then we have to divide by that new exponent. And then over here, we're going to add 1. So our exponent's currently 1. So that becomes 2. We divide by 2. And then since I have no bounds, we add our plus c. 1 over 1/2 is really the same as multiplying by 2. So I'm going to have a 2 over here. And then you have a choice at this point. You can solve for c right now. So we can plug in our conditions. So y is 25. So we'd have 2 square roots of 25 equals 3 squared over 2 plus c. And then you'd get 2 times 5, which is 10, minus 9 over 2 equals c. So 10 is obviously 10, and then 9 over 2 is 4.5. So 10 minus 4.5 would give you 5.5. You could also write it as 11 halves. It doesn't matter. Both would be equivalent. So now we have 2y to the 1/2 equals x squared over 2 plus, we'll just say 11 halves for now, because what we're going to do is we're going to now solve for y. So if we have 2 times y, we're going to multiply everything by 1/2 to cancel that on that side. So then you have y to the 1/2 equals, you have to multiply x squared by 1/2. So you get x squared over 4. And you have to multiply 11 halves by 1/2. So you get 11 fourths. And then that's a square root. So how do you get rid of a square root? You square it. So we have to square both sides. And we get y equals x squared over 4 plus 11 over 4 squared. And that is the solution or the expression for y equals f of x with that given initial condition. So here's just another example. We have dy dx equals x over y squared. And then what we did is I multiplied both sides by y squared. I left the x. You're going to integrate both sides. Your rule is to add the power and then divide by the power. And then you just work backwards and solve for y. This example did not have a condition, so we just got our answer in terms of a general. So this is called a general solution. So sometimes the directions will ask you to find the general solution of the differential equation. And all that means is that you're going to have a plus C in your answer. So if the directions ask you for a general solution, then you just need to know your answer is going to have a C in it. The other part of Unit 7 is slope fields. Slope fields provide a graphical way to visualize the behavior of the solutions to differential equations. A slope field gives us useful information about the solution to a differential. So we use slope fields and differentials. They go hand in hand because the slope field is a representation of the differential. So you learn them at the same time. We use them together. And then analyzing the slopes, which are the derivatives of the function, allow us to create that relationship back to the original function. So slope fields are kind of an enhanced way of seeing a differential equation in general, and then seeing it at a particular solution when you plot a point. So here's two different slope fields, and we're trying to determine whether A or B is the slope field for the equation dy dx equals the sine of x plus y. And we want to know which one is the positive and which one is the negative. So things you could ask yourself would be, okay, when would one of these equations be zero? Where would one of these equations be zero? So ideally, what you're trying to do in order to eliminate or find which slope field's correct is to try to find those particular points. So if you look here, this graph has an asymptote here, it has an asymptote there. This graph has an asymptote here and an asymptote there. And then what we'll also notice is that on this line here, they're negative, on this line here, they're positive, and then they're flip-flopped. So if you actually found the slope when y is 0, you could pick either a positive or a negative x value to help you see if it's positive or negative. So for me personally, I would probably pick a point on the coordinate plane here. So maybe I would pick 1 for my y value and 0 for my x. So I'd pick the point sine 0, 1. And I know that I'm either looking for a negative slope or a positive slope. So dy dx equals the sine of 0 plus 1. And dy dx equals the sine of 0 minus 1. So you get sine 1, and we get sine negative 1. So if you think about the value of sine 1, that's going to be positive. Why? Because sine, like the number 1, is in quadrant 1 in terms of the unit circle. So if you go back to like your unit circle days, here's 0, this is 1.57, this is 3.14, etc., etc. So if you picked a number where you're looking for sine 1, you're going to live over here in quadrant 1, which would mean that this is positive. If you pick sine of negative 1, well, that's like going backwards. So that's going to live down here in quadrant 4, which means the sine in quadrant 4 is negative, so this is negative. So that's just one way to help me figure out that this sign with the positive is A and the negative is B. So these are the questions we would go through and ask ourselves. This is the process by which you could help eliminate them. So again, one of my other suggestions was one of the graphs shows stripes with slope 1, the other one shows stripes with -1. So there you go. So here's kind of like the same work, but I wrote it down for you so we don't have to worry about that. So let's consider this slope field now. We have dy dx equals x squared, x to the fourth, parenthesis, y minus 2. On the axes, provide a sketch of the slope field for the given differential equation at the 12 points indicated. So you got to make yourself an XY table with the given points and the slope. So I always start in the bottom left corner here. So I'm going to start with -1. So we have -1, 0. So 0 minus 2 is -2. So that's going to be the value for all of the y's in that bottom column. What's going to change is our x's. So we have -1, 0, we have 0, 0, and we have 1, 0, all following suit for that bottom row. When you plug in -1 and +1, they're both going to be 1. So then you get -2 and -2. And if you plug in 0, you're going to end up with 0 times something, so that's 0. So a slope of 0 is a horizontal line, and a slope of -2 is going to be downwards like this. So that gives me my bottom row. And then the next row, your x's are going to be the same. What's changing is your y's. And again, what's kind of nice is the x's are always going to be the same value on the left and on the right side of the slope field, because a negative and a positive number to the fourth power are always the same. So 1 to the fourth and -1 to the fourth are both 1. And then when you plug in 1 for y, you get y minus 2, or 1 minus 2, so you get -1. So these both have a slope of -1. So they're just a little less steep than the one we already drew in. And then at 0, 1, you get 0 times something. So we get 0 again. Now we're going to do that for the next part. So remember, these 2 points are going to be the same. And again, anything times 0, so all of my zeros are going to be the same. Because you're always going to have x0 times a number, which is always 0. So I can actually quit looking at the zeros in my table. We're going to figure out the 2's, and we're going to figure out the 3's. So -1 and +1 are both 1's. So then you get 2 minus 2, which is 0. And then we plug in 3, so we get 3 minus 2, which is 1. So now we're at a positive slope. So we're going to try to make our positive slope the opposite of the red and make it 1. And there's our slope field. Part B, while the slope field in part A is only drawn at 12 points, it is defined at every point in the xy plane to describe all points in the xy plane for which the slopes are negative. So if you think about this, the slopes are going to be negative for all y values that are going to make that y minus 2 negative. So the slopes will be negative when y minus 2 is less than 0, because x to the fourth is always positive. And there you have it. dy dx will be negative when y minus 2 or y less than 2 Okay, so that was like part A and B for the free response question on an AP exam. Here's part C. It says consider that function, find the particular solution. So this is particular, which means I'm going to be given a condition, which means my answer better not have a C. If it said general, then your answer would have a C to the given differential equation with that condition. So we have dy dx equals x to the fourth y minus 2. And what we're going to do is move over the y minus 2. So I get 1 over y minus 2 dy dx. And we're going to move over our dx. So we have 1 over y minus 2 dy equals x to the fourth dx. And we're going to integrate both sides. And anytime you integrate that 1 over y minus 2, that's going to give you an ln. And over here, we're going to add 1, divide by that new power, and add r plus c. So at this point, you could find your c value now, or you can wait and you can find your c value at the end. It really doesn't matter. So let's say we waited and we e both sides. Then we get y minus 2 equals e to the 1/5 x to the 5th plus c. But again, we talked about how that plus c here can get brought down in front as my constant. So I get y equals c x to the 1/5 x to the 5th. We're going to add over that 2. And then what we're going to do now is find y of 0. So this is 0. And then we have our c, e to the 1/5 times 0 to the 5th plus 2. So that becomes c because e to the 0 is 1. So what that means is my c value is -2. So my particular solution is y equals -2 e to the 1/5 x to the 5th plus 2. Okay. So that wraps up that unit. So now what we're going to do is just look at a couple of our free response questions. So that we can continue our understanding of differentials. So let's start with the baby bird. The baby bird problem was a tricky one for kiddos the year that this happened. It says the rate at which a baby bird gains weight is proportional. So I see proportion. I'm like, all right, to the difference between its adult weight and its current weight at time t equals 0. When the bird is first weighed, it weighs 20 grams. All right, I'm immediately thinking, all right, initial condition. That's like b of 0 equals 20. So they already even kind of wrote that, but in my head, that's what I'm thinking too. And then it says, if B of t is the weight of the bird in grams at time t days. So sometimes like what I like to do, it says if B of t, so not dB dt, B of t is the weight of the bird in grams at time t days. So B of t, I just like right over here, I'm like B of t is grams. So then I'm like, okay, B prime of t, in case it asks me for units, is going to be grams, and then whatever t is, so days. So I'm just like, all right, I know my units. Let y equal bt be the solution to the differential equation with the given condition if the bird is gaining weight faster when it weighs 40 grams, or is it gaining weight faster when it weighs 70 grams? Explain. All right, so what do I need to do? I need to compare the rate of change. What's the rate of change? That's that given function right here. That's the rate of change, grams per day. So for part A, I'm going to find B prime of 40 and B prime of 70. Okay, so now 100 minus 40 is 60. 60 divided by 5 is 12. And again, that's grams a day. And then 100 minus 70 is 30. 30 divided by 5 is 6. So it's gaining more weight when it's little. So the question said, explain your answer. So I would say, because B prime 40 is greater than B prime 70, my baby bird is gaining more weight at 40 grams. Part B, find the second derivative. All right, so I gotta find my derivative. This is a function that I could easily distribute the 1/5. So dB dt is equal to 1/5. So 100 divided by 5 is 20 minus 1/5 b. So now the derivative of a constant is 0. So then my derivative is this. Well, that's negative 1/5. B represents a function. So that's going to be like B prime. But B prime is this. So then I'm just going to replace negative 1/5 with 20 minus 1/5 B. And then I'm just going to distribute. So that gives me a negative. 20 divided by 5 is 4. A negative times a negative is a positive, B over 25. So I got my D2B dt squared. Use that to explain why the graph of B cannot resemble the following graph. All right, so here's the following graph. So they're trying to say that this represents B double prime. We have to prove why it doesn't. So if I go down here and I look at my information given to me, I could find the zeros of the second derivative. So when the original equals 100, that's when I should have a potential CP, aka a point of inflection, because we're on the second derivative. So it's kind of like comparing 100 of the original. Well, the original is positive, so that tells me that this should be concave up. I have no idea what's happening after that. But we know at 20, so up in here, right, we know that the derivative is positive. So if you go back to my chart, right, so let's go to and investigate this so we can put this into words. So we're looking for a point of inflection, which we know happens here. And they're saying there's nothing down there. So this is increasing always, which would make sense, or it's going to increase always. If you talk about concave up and concave down with respect to this derivative, it's concave up when this is increasing and concave down when that's decreasing. Well, we have 12 and 6. So that shows decrease. So from 40 to 70, my rate's decreasing. And here, that would imply if this was concave up, that it was increasing. So we could say that because the graph is concave, you could go either direction, concave up, from, 0 to 20 days. It should have been concave down because b prime of t was decreasing. Okay, then I got to go on the back of my paper to do the next part. It says use separation of variables to find the original, the particular solution to this equation with a given initial condition. So we're going to take dv dt equals 1/5 100 minus b. We're going to separate our variables. So we're going to get 1 over 100 minus b equals 1/5 dt. We're going to integrate both sides. If you have 1 over a function, you're getting an ln. Since that's a constant, it becomes linear. We're going to isolate or get rid of the ln. I'm going to bring that c down in front. I'm going to solve for b. And then here's where it's a little tricky. I have a negative b. So that means that this is going to be a negative c value. So it's kind of like 100 minus CE to the 150, where that 100 sort of represents that starting idea. So we're going to put in, or our max idea, and we're going to put in our values. So we are told b of 0 equals 20. So that means that this is equal to 20. That's 0. So that zeroes out. This becomes a 1. We could flip them. And we get 80. So what that means is that b of t equals 100 minus 80 e to the 150. Okay, and then the second FRQ I wanted to walk through with you says consider the differential equation dy dx equals blah, blah, blah. Let's find the particular solution with the given initial condition. So part A says a portion of the slope field of the differential equation is given below. Sketch the solution through the point 0, 1. So here is our x, here is my y. So I'm going to go to 0 and then go to 1. So I like to give myself a nice big point on that graph. And then you're just going to follow the lines. So they go up and then they come back down. And then they're going down and then they're going over and then they're coming back up. All right, and I can kind of see that that looks like a sine graph. Not perfect, but you have that general shape, and it should make sense to us that if this is the derivative and it has a cosine, then the function before it will have a sine, and I can definitely see a little bit of that sine curve. Over here, I might have gone a little wonky. I might have needed to look a little bit more like that. But they're not going to be that picky. They're looking for, did you go through this point and did you follow the curve from beginning to end? So part A. Part B, write an equation for the line tangent to the solution curve in part A at point 0, 1. So, all right, I need my slope at 0, 1. So what I'm going to do is plug in 0 and 1 to my original function. So that gives me my slope. Oh man. Beep. Sorry, kiddos. 0 is x, 1 is y. I had. Okay, so cosine of 0, well, that is just going to be 1. So you get 2. So the slope at that point is 2, and I can almost see that in my graph, right? Sorry. I can almost see that in this graph. This definitely has a positive slope. It could be 2. So that makes sense logically. So then my equation of a tangent line is y minus y1 slope x minus x1. So you get y equals 2x plus 1. So we're like, all right, I got this. And then it says approximate 0.2. So that just means I'm plugging 0.2 in for x. And 0.2 is really the same as 1/5. You could say it's the same as 2/10, but I like to put it as a fraction so it's easier for me to see 2/5 plus 1 because I know that 2/5 is 0.4. But again, you could multiply 2 times 0.2 and also get 0.4, and you get 1.4. And it says find the particular solution. So for part C, you're just going to take dy dx equals 3 minus y cosine x. We're going to get the x's on the right, the y's on the left. We're going to integrate. Antiderivative of cosine is negative sine. Okay. So then at this point, you would both sides, or you can plug in your initial conditions. So it really doesn't matter. It's kind of up to you how you want to follow it or do it. So I have a tendency to plug them in here because I think it's a little bit easier. So I'm going to plug in my 0 and 1. Sine of 0 is 0, so that cancels out. Negative 1 plus 3 is 2. So I get that the c value is equal to the natural log of 2. So then going back to my original function, I have natural log of negative y plus 3 equals negative sine x plus natural log of 2. Now, we have to determine which way my negatives are going to go since this is an absolute value. And since my sine's negative, but I can tell in that curve that it's positive, we're going to take the negative natural log so that that will eventually cancel out and turn them back to a positive. So it's negative the natural log of negative y plus 3 equals negative sine x plus natural log 2. And another way is to think about since y of 0 equals 1, then we need our y values to be less than 3. So again, we need them to be the negative part. So divide both sides by negative 1. Both sides. Subtract. You can bring that down if you want. You can leave it up. Doesn't really matter. We're going to change our signs one more time. So when we subtract, we get negative 3, but we got to get rid of that negative on y. So it's going to become positive 3 minus e to the sine x minus ln 2. And again, you could bring that down in front if you would like. And when you bring it down, that's really like e to the sine times e to the negative ln of 2. So the negatives and the ln's and the e's are all going to kind of cancel out. Otherwise, there you have it. So what I have left for you for today is that we are going to go to Delta Math. You had a Delta Math assignment yesterday. There's a couple Delta Math questions out there today. And then I also have created a quizzes with multiple choice. So what I did for the quizzes was determine which AP exam it came from, calculator or non-calculator. And if it's calculator, you get 3 minutes. If it's non-calculator, you get 2. So that's how the quizzes points went. So whoever comes in first, second, and third will get our bonus points for that quizzes. So I'm going to post that code on our page now. It's also going to be posted up here right now. So you can see here's that code. Let's do a new share with just that portion so you don't have to see everything crazy. So you can see on this that it's a unit 1 to 6 review. So that's everything we've been doing for the past few days. And then the idea is that it is due tomorrow before our class time. And April 28th. Maybe that's the time I posted it. That's not due tomorrow. Oh, here we go. Deadline. 7:45 tomorrow morning. That must have been when I posted. Okay, so it's due before school so that you're not trying to work on this in another class period. And that way we can go over it in class, talk about the questions. Some of them are just general knowledge. Some of them are AP questions. So you have the remainder of class time today to do that quizzes. And then, like I said, there is a new Delta Math assignment out there for you. So it's on slope fields. So your questions are going to be on slope fields, tangent lines, differential equations, and evaluating exponentials at particular points, tangent lines like we just did in that problem, and definite integrals. So those are our 2 reviews for today. When we come in tomorrow, we're going to do area, and more area. And then hopefully we can spend our last few days of class reviewing everything. Questions, comments, concerns, anything you struggled with from yesterday, anything you missed today and need to see?
I'm good. Have a nice rest of your day.
Okay, let's do this. How do you feel now about slope fields compared to before? So go ahead and give me a reaction and then let me know if you need anything from me in chats. So Maddie, you feel good, 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 good. Okay. All right, guys, then I'm going to release you and let you go start on your assignments.